Let's talk about the fundamental concept in natural language processing, which is embeddings. Embeddings represent words, sentences, or even larger chunks of text as vectors in a multidimensional space. This transformation allows AI models to process and understand human language more efficiently. First, let's talk about word embeddings. These are techniques that map words to vectors, capturing their meaning and relationships. Word-to-vec is a popular method that learns words' relationships through context. For instance, if we take the words king and queen and the words man and woman, Word2Vec can understand that the relationship between king and queen is similar to the relationship between man and woman. This is achieved by analyzing large text corpora, allowing the model to understand that king is often associated with queen, just as man is associated with woman. GLOVE or global vectors for word representation utilizes global word co-occurrence statistics to create the embeddings. Imagine reading an entire book and counting how many words appear together. GLOVE captures these co-occurrences frequencies to understand relationships. For example, ice and water frequently appear together, indicating a strong relationship, whereas ice and fire rarely do, indicating a weak relationship. Fast text improves on word-to-vec by embedding subwords. This means it can handle out-of-vocabulary words better, as it breaks words into smaller parts and learns from them. For example, if the model encounters the word unhappiness, it can break it down into un, happy, and ness, and understand its meaning even if the exact words were not in the training set. Moving on to sentence embeddings. These techniques represent entire sentences as single vectors, capturing their overall meaning. One simple method is averaging the embeddings of individual words in a sentence. For instance, to embed the sentence, the cat sat on the mat, we average the vectors of the words the, cat, sat, on, the, and mat. While straightforward, it can lose some contextual notions. Sentence transformers use deep learning models to encode entire sentences. These models, such as BERT, capture more complex relationships and contexts within sentence. Given the sentence, "The bank will not approve your loan," the model understands that the bank refers to a financial institution and loan relates to borrowing money. Developed by Google, the Universal Sentence Encoder is a pre-trained model that provides robust sentence embeddings for various NLP tasks. For example, it can be used to embed a customer review and determine whether the sentence is positive or negative based on the encoded vector. Next, we have contextual embeddings, which capture the meaning of words within their specific context. BERT, or bidirectional encoder representations from transformers, reads text bidirectionally, understanding words in context both before and after them. For example, in the sentence, "He went to the bank to deposit money," BERT understands that bank refers to a financial institution because of the context provided by deposit money. Robert A stands for Robustly Optimized BERT Pre-training Approach. It improves on BERT by using more data and longer training periods. This results in better performance on language understanding tasks, such as comprehending complex sentences in legal documents or scientific articles. ExcelNet combines the strengths of autoregressive and autoencoding models, providing better performance in language understanding tasks. For instance, ExcelNet can accurately predict the missing word "quick brown fox jumps over the lazy dog" by understanding the broader context. Embeddings are crucial in transfer learning, where pre-trained models are leveraged for new tasks. Fine-tuning involves adjusting pre-trained models to perform specific tasks by training them on labeled data related to those tasks. For example, a pre-trained language model can be fine-tuned to improve its performance in customer service chatbots. In feature extraction, pre-trained models are used to generate embeddings that serve as features for other models. For example, embeddings from a pre-trained BERT model can be used to improve the accuracy of a sentiment analysis model. Fine-tuning pre-trained embeddings involves several steps. Prepare labeled data for the target task, ensuring it is representative and comprehensive. For example, collecting customer service dialogues to fine-tune a chatbot model. Model selection. choose a pre-trained model that best suits the task at hand. For instance, selecting Robot A for tasks requiring deep contextual understanding. Parameter optimization. Optimize the model's parameter on the target data to improve performance. This includes adjusting learning rates and training epochs to achieve the best results. Evaluating embeddings and fine-tuned models involves several matrices. First one is accuracy. Measures the proportional of correct predictions. For example, determining how often a sentiment analysis model correctly identifies positive and negative reviews. Second is precision. It indicates the accuracy of positive predictions. For instance, measuring how accurately a spam detection model identifies actual spam emails. Third is recall. It shows the percentage of positive cases correctly identified. For example, evaluating how well a medical diagnosis model identifies all cases of a particular disease. Last is F1 score. This is the harmonic mean of precision and recall, providing a balanced evaluation. This metric is crucial in scenarios where both false positives and false negatives have significant consequences, such as a fraud detection. Combining text with other data modalities like images and audios is called multi-modeling embeddings. For instance, creating embeddings that link text descriptions to corresponding images in a dataset. In cross-lingual embeddings, it represents text in multiple languages, aiding in translation and multilingual tasks. For example, developing models that understand and translate between English, Spanish, and Chinese. In explainable embeddings, it understands and explains the reason behind embeddings to improve transparency and trust. For example, creating models that can explain why a particular piece of text was classified as positive or negative. Embeddings are a cornerstone of modern NLP, enabling powerful AI applications across various domains. From word to sentence and contextual embeddings, each type offers unique benefits and challenges. As we continue to innovate, embeddings will play a crucial role in advancing AI's understanding of human language.